Hi, welcome to Calculus. Today's lesson is integration of rational functions by a process called completing the square. And in order to see the formulas you're going to need for today, you're going to want to be looking at the practice worksheet 8-4 that's available on Google Classroom. And our concept for today is going to help us to find certain types of derivatives when you have a quadratic polynomial in the denominator or a quadratic polynomial that's under a square root in the denominator of a fraction. And again, the process is going to involve two formulas. They're found on the practice worksheet. One is going to give us an answer that is an arctangent case, and the other type is going to give us the arcsine case. In fact, the one without the square root in the denominator will always be the arctangent case, and the one with the square root will be the arcsine case. Example number 1 on the practice worksheet. The integral of dx over x squared plus 2x plus 2. The denominator of this fraction is a quadratic trinomial because it has the highest power of 2. So I'm going to review the process for completing the square. Your quadratic equation is in the form ax squared plus bx plus c, and it's x squared plus 2x plus 2. The goal is to get the first two terms of this polynomial to be a perfect square trinomial. So the general format of this is to let c equal b over 2 squared. And this particular problem, b is 2. So it's going to be 2 over 2 squared, which is 1 squared, which is 1. So I'm going to rewrite my polynomial as x squared plus 2x plus 1, but because the original problem said plus 2, we're going to add a 1 at the end so that the last two terms equal 2. The first part of this is now what's called a perfect square trinomial. And if I take my b value and I cut it in half, that's always going to be the term that we put inside the parentheses. So x plus 1 quantity squared, if I was to multiply that back out, I would get x squared plus 2x plus 1, and I bring down the plus 1. This is how I'm going to want to rewrite my denominator in my integral. So going back to the original problem, we now have dx over, and I'm going to reverse this so that it fits the form, 1 plus x plus 1 quantity squared. And if I have something in this form, you'll notice that it matches the arctangent form. I have an integral of a du, or in this case dx, over a squared plus u squared, where my u is x plus 1, and a is what I squared to get 1. So u is x plus 1, a is 1, because that's what I squared to get 1. And to write my final answer to the problem, all I need to do then is write 1 over a, which in this particular problem was 1, times the arctangent of u over a, which is x plus 1 over 1, plus c. And just to clean that up a little bit, I don't really need the 1 over 1 out in front or the 1 underneath, so I just get arctangent of x plus 1 plus c. Example number 2. I have the integral of 5 over the square root of negative 2x squared minus 8x minus 6 dx. And once again, I have a quadratic polynomial, trinomial in the denominator. It's under a square root though in this case, so we're going to try to make it fit the arcsine form that you see on the practice worksheet. So once again, to complete the square, I want to take negative 2x squared minus 8x minus 6, And during the completing the square process, you always factor out any coefficients to the left of x squared first. So I'm going to pull a negative 2 out in front. That will leave me with x squared plus 4x plus 3. I want my c value to be b over 2 squared, which in this case b is now 4 after I factored the negative 2 out in front. So I get 4 over 2 squared, which equals 2 squared, which equals 4. So I have negative 2, which I had already factored out in front, and now I'm going to write x squared plus 4x plus 4, but because it really should equal plus 3 according to what I had in the previous step, I put a negative 1 after that, so that the last two terms equal 3. I can now rewrite this trinomial as a perfect square trinomial. It's going to be x plus 2 quantity squared. It's always going to be half of whatever the middle number is. And then minus 1. And one last thing I'm going to do here, I'm going to make this negative 2 into a positive 2 by factoring a negative 1 out of the quantity inside the brackets, which will leave me with a positive 1 minus x plus 2 quantity squared. So I now want to rewrite this over where I had my original integral. And I have the integral of 5 over, and this would all still be under the square root symbol. I'm just going to break it up into two parts though. I'm going to make it square root of 2, because that would be under the square root symbol, and then square root of 1 minus x plus 2 quantity squared dx. The 5 over root 2 can be factored out in front. And I now have just dx over the square root of 1 minus x plus 2 quantity squared. My u value in this case would be x plus 2. My a value would be what I would square to get 1, which is 1. So the final answer to the problem will be the 5 over root 2 that we had originally. And then this will be the arc sine case. So we put arc sine of u over a. U is x plus 2, a is 1, so that'll just be x plus 2 plus c. Example number 3. The integral is 1 over 5x squared minus 30x plus 65 dx. And once again, we have a quadratic polynomial in the denominator that does not have a square root over it, so this is going to be the arctangent case. To complete the square, we first factor the 5 out in front. And my b value this time is a negative 6, so it's going to be, again, b over 2. C is equal to b over 2 squared, which in this case is negative 6 over 2 quantity squared. Negative 6 divided by 2 would be negative 3. When I square that, I get 9. So I want my c value to be a 9 in this case. So I write x squared minus 6x, keeping the 5, of course, on the outside, plus 9. But because it needs to equal 13, if I add an additional 4, it will equal 13. The trinomial that we have at the beginning is now a perfect square trinomial. It is x half of b, and b is always what you get after you factor the constant out in front. So b is negative 6, half of that is negative 3 quantity squared plus 4. So when I now rewrite my original integral, I now have 1 over 5 times, and I'm going to reverse this once again so that it fits the form, 4 plus x minus 3 quantity squared dx. My u in this case is x minus 3. My a value is what I square to get 4, which would be 2. And I still have this 1 over 5 that I need to factor out in front, so I'm going to end up with an answer of 1 over 5 And this is the arctangent case, so we have to make sure we remember to put that extra 1 over a out in front, only for the arctangent case. It's going to be 1 over 2 arctangent of u over a, and that happens to be the same for arcsine as well. It's always u over a. So it's u over a, which is x minus 3 over 2 plus c. And the last thing I can do is just multiply that 1/5 times the 1/2 to get a final answer of 1/10 the arctangent of x minus 3 over 2 plus c. Example number 4. The integral of dx over the square root of 21 minus 4x minus x squared. This again is going to fit the form of the arcsine because of the square root in the denominator. So to complete the square, I'm going to first factor a -1 out of the trinomial in the denominator, which will make it positive x squared, positive 4x, and negative 21. My c has to equal b over 2, which in this case is 4 over 2 squared. That's 2 squared, which is 4. And that allows me to rewrite my expression now as x squared plus 4x plus 4. But in order to get down to a negative 21, I would have to subtract off 25. And once again, if I have a negative number on the outside, I'm going to factor a -1 out in front. So I'm going to have a positive 1. And I'm going to reverse this and make it 25 minus, and if I rewrite this trinomial as a perfect square, it's going to be x plus 2 quantity squared. Because again, it's half of b, x plus 2. So when I rewrite my integral now, I get the integral of dx over, remember this is still under the square root, 25 minus x plus 2 quantity squared. My u value is x plus 2. My a value is what I square to get 25, which is 5. And because this is the arcsine case, I don't need a fraction out in front. I just get the arcsine of u over a, which is x plus 2 over 5, plus c.